Alright guys, we're going to get started with the Snack Tectonics lab. You need to have a few supplies out, including your lab document, lab slides, and this lab video ready to go. Alright guys, we are going to be doing the Snack Plate Tectonics lab. Since unfortunately y'all are not in class with us, I wanted to make sure you at least got to have a little bit of fun with the lab, so I recorded a video for you so you can kind of follow along and see what we did. And if you happen to have all of these total kitty snack foods at home, you are welcome to do the lab yourself as well. You'll need icing, which is going to act as our asthenosphere, or the melted part of the mantle. You are going to need crackers. In this case, I'm using graham crackers that are going to act as the continental crust, and you are going to need fruit roll-ups, or if you have, I guess, the fruit by the foot, I've used that before, it kind of works. Something like that, some flat fruity thing, you can use that as well. So that is going to act as our oceanic crust. And of course, because he's cute and he's awesome, I have Baby Yoda fruit roll-ups. All right, so our objective for this lab is going to be to use models, to describe how tectonic plates cause major geologic activities such as ocean basins, earthquakes, volcanoes, and mountain building. So the questions that we want to keep in mind is, how does this model help us understand plate movement, and how do the movements of tectonic plates cause geologic events? So we are going to start by modeling a divergent plate boundary. So I'm going to move my continental crust out of the way over here, and we are going to start with our oceanic crust, which is going to be our fruit roll-ups. So I am going to put our fruit roll-ups on top of our asthenosphere, or I should say our oceanic crust on top of our asthenosphere, Baby Yoda and all. And notice I just created a plate boundary right down the middle of the fruit roll-up here, where these two oceanic plates come together. But our job is to actually make a divergent plate boundary, so they should be moving apart. And I will show you how that is going to happen in just a second. So with divergent plate boundaries, what they do is they separate. So I'm going to move our fruit roll-ups apart and hope I don't get completely stuck to them. And notice what has happened. Our asthenosphere, our icing, has been exposed by that divergent boundary. So remember that our frosting is representing that melted part of the mantle, the asthenosphere, and then our fruit roll-up is representing oceanic plates. So what I'd like for you to do is pause the video, and I want you to take a screenshot using your snipping tool if you have a school computer, or if you are working at home. I know some of you have Mac computers. You can use the preview program to take a screenshot, and you're going to paste it into your lab. So please pause here, go ahead and get that screenshot of our awesome divergent plate boundary. All right, now that you are back, what I would like for you to do is answer the reflection questions that are on your lab paper. So the reflection questions include: when divergent plates pull apart, how is new crust being made in this lab? And then review the divergent plate boundary information on the slides. There's some information about mid-ocean ridges, an example of that being the Mid-Atlantic Ridge, which we talked about in class. If we're on land, this might be a rift valley, and your slides for the lab are going to include that. So you should be reviewing those slides. All right, our next type of boundary that we are going to do is a continental oceanic collision. So I am going to remove one of our oceanic plates here, and we are going to replace it with a continental plate. All right, I'm going to start with them close together. So we've got our plate boundary right where my finger is here, and we can see our continental plate, which is less dense, is sitting next to our oceanic plate. And what we're going to see with an oceanic continental collision is a convergent plate boundary. They're going to come together, and watch what happens. So if I push on this plate, notice it is actually going up over our oceanic plate, up over our fruit roll-up here. So what has happened is our fruit roll-up, our oceanic plate, has been subducted. We just created a subduction zone. If you could see it from this angle down here, you'd actually see that this has become a little bit lifted up, the graham cracker side, which is our continental plate. So the subduction zone, the oceanic plate subducted under the continental plate, our graham cracker here. And this was a convergent boundary. So they've collided together and created a subduction zone. So what this would actually create is right where my finger is, right here on the edge. This would actually create a trench here in the ocean. This could also create mountains or volcanic activity here. And if everything was underwater, we might actually even have island arcs form kind of out on this end as well. So what I want you to do is same thing as last time, pause the video here. Go ahead and take a picture of this using, again, the snipping tool or your screenshotting tool on your computer. So do that now, please. Add it into your lab. All right, now that you've added your picture into the lab, you are going to answer the reflection questions, which one of them is when continental crust and oceanic crust collide, one plate goes under another. Explain why the process of subduction occurs. So tell me about subduction on your lab, please. Go ahead and scroll through the remaining slides of your lab. You'll see a little bit more about subduction boundaries. It's going to talk about some of the examples that we have in the real world, such as the Aleutian Islands of Alaska. I've got some pictures of those for you as you scroll through. You'll read a little more about subduction when it occurs near land and also on an oceanic plate, kind of similar to what we had happen with this one. And you'll see that things like the Andes Mountains and volcanic arcs can form. So again, read through that and answer your questions. All right, guys, now for our next type of plate movement. I've kind of mushed my icing back together here. I might have eaten a little bit in the intervening time and had to make it a little bit thicker for our next one. So what we're going to do here is a continent-continent collision. So for this one, we are kind of get a little gross here. We are going to actually take our crackers and we're going to put them into a little bit of water for just a second. We need them a little bit mushy for this to work. All right, so I've wet this one. I'm going to stick it right here. And then my one that had icing on it, stick it in the water as well. And I'm going to put wet edge of cracker to wet edge of cracker. Okay, so we're going to do a continental crust collision. This is going to be a convergent boundary. We are going to push our graham crackers together in just a minute. Remember, our frosting again is a stenosphere. Our graham cracker is acting as continental crust. All right, here we go. All right, notice our crackers just buckled. If you could see it from this side, this center part is actually lifted up quite a bit right there. So if I keep from getting icing all over everything. What we see is these wet edges have buckled up. So I want you to, again, pause the video like we did for the last round. If you can get a snapshot using, again, your sniffing tool, or if you're on a Mac, the Freeview program, and get that inserted into your lab, and then you need to go answer your reflection questions. So pause here, get your picture. All right, now that you're back, you need to go answer your reflection questions on your lab, which this one is in our model. The wet edges of the cracker buckled or folded, and they did lift up. Let me see if I can give you a better view here. I'm going to try to lift these up just a little bit. There you go. You can see they buckled like that. All right, so what geological event does this buckling mimic? So if this actually happened on land, ooh, that's squishy, and these two crackers came together, what is the squishy part right here? What did I just make? So why do you think this event occurs in real life is the second question that you have there. Then what you're going to do is continue scrolling through the lab slides, and you are going to look at a little bit about continental convergence. It's going to talk a little bit about how that subduction zone forms and how that is a type of convergent plate boundary. All right, so I'm going to remove these here, and we are going to go on to transform boundaries. I'm going to have to get rid of some of the gooey part of the cracker. And we are going to flip around and use our dry parts of our cracker. There we go. All right, so our last one is taking a look at the transform plate boundaries. And remember, transform boundaries kind of go side to side instead of up on top of each other or pulling away from each other. So for this one, watch what happens. Okay, if this was real, this would be like earthquake, and they would slide past. So once they finally get loose from each other, there's a lot of pressure that's released, which causes the actual earthquake. They go in opposite directions, but they're still kind of level with each other. They're not falling apart or coming together. They're just going right past each other. So this is our transform boundary. So again, go ahead and pause, take a picture, add this into your lab. All right, now that you're back, you need to answer your reflection questions. What happened to the dry edges of the cracker? Remember, I kind of like had them stuck together a little bit and then they went. All right, and how is this model similar to what happens in an earthquake? Once you're done answering those questions, or to help you answer those questions, you may want to scroll through some more of the slides, read a little bit more about transform boundaries, how they cause earthquakes, how the San Andreas Fault is actually a transform boundary, and then answer any remaining questions in your lab. There should be a few follow-up questions in there, and make sure you very clearly understand the difference between convergence, so coming together, divergence, coming apart, and transform, sliding past each other one way or the other. All right, guys, thank you for completing the rest of your lab. Once you are done, if you can make sure you go on Canvas and get that submitted. If you need to rewatch any sections, go right ahead. And I hope you guys at least had a little bit of fun with me playing with my food.